Today we will move on to chapter number 8, fluid dynamics, and we will particularly see about flow systems. Okay, so in this chapter, we will have two subtopics mainly. So the first subtopic we will be seeing about momentum analysis, and the second subtopic will be on internal flows in pipe. This chapter with 8.1 Newton's law. What is Newton's law? So Newton's law relate between motions of body and the forces acting on them. So practically we will be studying on the bodies, so any bodies that will be in motion, and what are the force acting on it, okay, that causing the motion. Okay, so Newton's law can be divided into few laws. Okay, the first law will be a body at rest remain at rest and a body in motion remain in motion at the same velocity in a straight path when the net force acting on it is zero. So, when the body is at rest, it will be remain at rest. So meaning there will be no force acting on it. And when a body is in motion, okay, for example in a boat or in a car, so our body is in motion and there are no force acting on it, then the body will be remain in motion. So that is what Newton's first law is saying. So therefore, the body tends to preserve its state of inertia. So when the body is in motion, so it will be remain in motion according to the Newton's first law. So and when we suddenly stop the motion, so that's the reason why our body will tend to go front and back, okay, when we suddenly stop a car. So that is because of the state of inertia. And Newton's second law is saying that the acceleration of a body is proportional to the net force acting on it and inversely proportional to its mass. So according to this relation, so the acceleration is directly proportional to the force. So meaning if the acceleration increase, the force will be increasing, but inversely proportional to the mass. So acceleration increase when the mass is reduced. So it will be opposite. So there is another law under this Newton. So Newton's third law. So it is saying that when a body exerts a force on a second body, the second body exerts an equal and opposite force of the first. So meaning the direction of the reaction force depends on the body taken as the system. So Newton's third law basically what is saying, when you are applying a force, so there will be equal amount of force from the opposite direction. The actions will have a reaction. So that is what uh, Newton's third law is saying. So this is a summary of Newton's law. So if we see Newton's second law, as we saw earlier, so the famous formula that we will use for Newton's second law is F equals to ma. And if we change the form, so acceleration is actually dv over dt. So the changes of velocity over time, and we also can incorporate m inside, so the mass inside, because the mass is it's a constant. Okay, so it can be represent in such a way. So m, uh, so we can relate it with the velocity in terms of acceleration, and we also can have mv, which is the momentum. So we can relate it based on the momentum. So linear momentum or just the momentum of the body. So what is momentum? So momentum is actually the product of a mass and the velocity of a body. So if a mass times with velocity, that is a momentum. Okay, so Newton's second law is usually referred to as the linear momentum equation. So we also can relate. So Newton's second law is F equals to ma. So we also can convert it into a linear momentum equation. It can be referred as that. The conservation of momentum principle. Okay, the momentum of a system remain constant only when the net force acting on it is zero. So the momentum will be the same if no additional force is acting on it on the system. Okay, so F is the net force and dmv over dt is the rate of change of. So Newton's second law for rotating rigid body is expressed as m equals to I alpha. So earlier we have seen on the linear motion, so meaning front and back to sideways, so that is considered like a linear. So if a body is having a rotational motion, then we need to use this formula. So this formula is almost similar like F equals to ma, but in a rotational form. So we will use for F, we will have a m. So m is the net moment, or we call it as a torque. So torque is the turning effect of force, and I is the moment of inertia, and alpha is the angular acceleration. So practically the components are the same, similar like the linear, but in a rotational we have different abbreviations. Okay, so similarly it can be converted into various form. So relating it with the angular velocity, so I d omega over dt. So omega is the angular velocity in radian per second, and we also can incorporate I inside, and we can convert it into dh. H is the angular momentum. So all these are possible if the body is mentioned that it's rotating in a circular motion. Okay, for a rigid body rotating above a fixed x-axis, the angular momentum equation is so x is the x-axis. So mx equals to ix d omega x over dt. So this formula equals to dhx over dt. So we can calculate for one particular axis. So angular momentum equation. So the rate of change of the angular momentum of a body is equal to the net torque acting on it. So m is the net torque. So dh over dt is the rate of change of angular momentum. So as we can see. Okay, so choosing a control volume. A control volume can be selected as any arbitrary region in space through which fluid flows, and its bounding control surface can be fixed, moving, or even deforming during a flow. So we can choose a control volume for our analysis. So it can be a fixed fluid flow, so it can be a moving, or even a deformation happen during a flow. So many flow systems involve stationary hardware firmly fixed to a stationary surface, so like this. So maybe it's a fixed body, uh, and the surface is stationary, and such systems are best analyzed using fixed control volume. So the fixed control volume is much easier to analyze. So similar like this. So this is your control volume. So we can know the mass entering and mass going out. So the pressure entering and pressure going out. So it will be much easier for us to analyze, and it will be much harder to analyze when it involves a flow system that are moving or deforming. So like an aeroplane. So aeroplane so is a uh, control volume. So control volume because the aeroplane is not expanding or shrinking, but it is moving. So aeroplane is moving from one place to another place. So we consider it as a flow system that is moving or deforming in the case of like a piston. So the control surface is expanding and shrinking. So we can consider it as a deforming. So it is usually more convenient to allow the control volume to move or deform. Okay. So it can be analyzed, but just more factors must be calculated in order to understand the analysis. In deforming control volume, part of the control surface move relative to other parts. Okay, so like this, a piston. So it is having a deforming control volume because it's expanding or shrinking. So part of the control surface moves relative to the other part. So like in this case, is related to the piston. So when the piston move down, so it expands. So when it moves up, it is shrinking. Okay, so it will move related to other parts. Okay, so 8.3 forces acting on a control volume. So there are various forces, type of forces that they will be acting on a control volume. So we can divide it into few. Okay, so the forces acting on the control volume consists of body force and also surface force. So body force is the force from the body, so experienced by the body, and the surface force is the force acting at the surface of the control volume. So this is the control volume. So you have a mass and it has a body, and the body is experiencing some force, and the surface is at a particular area that we have selected to the analysis. So the body forces that act through the entire body of the control volume. So the body force is acting on the entire body. Okay, and so for example, like gravity. So gravity will be acting on a particular body, in the whole body, the entire body, and the electricity. So electricity passing through a body. So yeah, it can be the whole body, and also can be the magnetic force. So all these are considered as a body forces. Then at the same time, we also have a surface forces. So surface forces acting on the control surface. Okay, so it can be like in a form of pressure. So it can be a viscous force. So it can be a reaction force that we can calculate at the point of contact. So the most common body force is that of gravity. So gravity is something that we experience naturally, because when we already in the earth, earth uh, environment, so gravity is already acting on all the bodies. Okay, so we consider it as a body force. So it is generally is a downward force, because is pointing towards the core of the earth, because the core of the earth is the one that causing the gravity to happen. So it will be a downward force towards the earth core, and every is a force acting on every differential element of the control volume. So in a control volume, you can have various elements. So gravity will be acting on all the elements. These are some of the formula. So force of gravity we can calculate based on rho g dV. So the changes in the volume. So we can find the changes in the gravitational force and F body. So if we integrate it, so we will get the mass of the control volume times with gravity. Okay, surface forces. Earlier we have seen on the body forces. So what is surface forces? Surface forces are not as simple to analyze, since they consist of both normal and tangential component. So it will have two components, so normal and also tangential. So normal stress uh, are composed of pressure, so which is acting towards the body, okay, from outside. Okay, so it acts inwardly. Inwardly normal meaning towards the body, and viscous stress. Shear stress or tangential stress are composed entirely of the viscous stress. So it's on the same line with the line of action the body. Okay, so surface force we can divide into three. So it can be on the force because of pressure, it can because of viscous, and also the other types of force. So it's composed of all these elements. So the other force is composed of reaction forces required to turn the flow, forces at balls, uh, cables, struts, or all through which the control surface cuts, and so on. So other types of forces are some mostly will be negligible, but at times if the force is must be taken into consideration, then you need to add it under the other forces. So you can see here the equation. So summation of F equals to summation of F body plus summation of F surface. So the if we divide it into the components, so the F body, so the force on the body is actually the gravitational force, plus with the surface force is consists of all these three: the force because of pressure, the force because of the viscous condition, and also the other forces. So all the summation of the total force must be consists of all these four elements. Okay, a common simplification in the application of Newton's law of motion is to subtract the atmospheric pressure and work with gauge pressure. So I think we have seen this in the previous lectures. So when we need to uh, disregard or subtract the atmospheric pressure, because when you can see the reason here. So why we can subtract the atmospheric pressure and we only work with the gauge pressure, because atmospheric pressure acts in all the direction. So if a surface is exposed to the atmospheric pressure, so the surface that exposed, so you can disregard the atmospheric pressure in your calculation. So here you can see, so you have a body, so body with a weight W, and a force is acting on to the left. So the green arrows here, the small arrows, so indicating the atmospheric pressure. So we can see here atmospheric pressure is acting on all the direction. So what will happen? So its effect cancel out in every direction. So meaning if you have a force atmospheric pressure in this direction, so there will be the, another atmospheric pressure in the opposite direction because it is exposed. So after some time it will cancel each other. Okay, so it will cancel each other, and you can just consider the gauge pressure. So meaning it will start from zero. So like how we use the apparatus or the pressure gauge to measure. So it will start from zero. So it will be similar. So it will simplify your calculations. Okay, so 8.4, the Reynolds transport theorem. So there's a theorem related to Reynolds. Uh, this is because related to the can, spray can. Okay, so we can analyze the spray or the deodorant from a spray can using a two method. So the first method, we follow the fluid as it moves and deform. This is the system approach. No mass crosses the boundary and the total mass of the system remain fixed. So we we analyze the fluid in the can. Okay, so as it move and deform, and but you're not pressing anything the can, and so nothing goes out of the can. So the total mass of the system is fixed. So we can analyze the particles inside. And the second approach, we consider the fixed interior volume of the can. So we have a can here, Okay, so it's fixed interior volume, uh, but you can press it and the spray can go up. So we call it as a control volume approach. Okay, so the relation between the time rates of change of an extensive property of a system and for control volume is expressed by Reynolds transfer theorem. So, so you have a system. So you have a system, and you also have a control volume. So in between, it is related by Reynolds transfer theorem. So it will communicate between the system and the control volume. Okay, so if there's any changes, so it will moderate the changes. So in order for us to analyze. Okay, so 8.5, the linear momentum equation. Okay, linear momentum equation. So we know it is mv. So it is coming from Newton's second law. And for a system of mass m subjected to the net force summation of F is expressed as, so we know Newton's second law is F equals to ma. So we can convert it like how we seen in the previous slides. So m dv over dt is equals to d dmv over dt. So noting that both the density and velocity may change from point to point within the system, Newton's second law can be expressed more generally. So if you know that the the force is not constant and the density and velocity keep on like changing, then you can take the integration of a few points. So point 1 to point 2. So you take uh, the values, then point 2 to point 3. So you add up. So add up. So that's why it's an integration. Then you can calculate the net force change. So Newton's second law can be stated as the sum of external forces acting on a system is equal to the time rate of the system of linear momentum of the system. So so we can take a B as the linear momentum. So linear momentum we know mv. So we can, so let's say B, smaller b uh, is the derivation that we want to investigate. So from here b equals to mv. So if you want to only find v, so you bring the m down. So b over m equals to v. So based on that, so we can derive this formula, and you just replace it with with all this information, and at the end we'll get the summation of f equals to the changes in rho v dv times with plus with the changes of rho v times n dA. So this is from chapter 7. Okay, so if you don't understand how you get this, so you can refer back to chapter 7. So we already discussed this before. And at the end, so what is it is actually saying, the sum of all external force acting on a control volume, so summation of F, is actually the time rate of change of the linear momentum of the contents of the control volume. So this is a time because it is related to t. So how much in one particular time the linear momentum of the system change. So that's the first part, plus with the net flow rate of linear momentum out of the control surface by mass flow. And so this is the rate of net flow rate of linear momentum that is going out of the control surface uh, by a mass flow. Okay, so with that, we conclude chapter number 8. So today we have discussed on Newton's laws. So there are three laws. So make sure you understand what is Newton's law. Then we have discussed on how to choose on choosing the control volume. Then we have seen the forces acting on a control volume. Then the Reynolds transport theorem, and also at the end the linear momentum equation. So with this, I would like to conclude this lecture. So thank you for listening.